Okay, we'll continue the discussion about gears and gear transmissions. We looked at the first part of the chapter 11. That's on bankruptcy. And today we're going to discuss about gear transmission calculation. Now I'm behind writing text and equations for this part of the notes. What I did, I took some screenshots of scanned handwritten documents, and I'll be discussing those. So let me open up the first of them, and of course it has to be within the recording box. Okay, transmission ratio calculation of simple gear trains. This is pretty basic for the subject on gear design. Let me reduce the size. Oh, maybe this is too small. And you cannot, can you? I believe so. No, it's fixed size. Anyway, so I'm going back to zoom out. So zoom out, and let's see what we can make out of this. So what we're looking at here is a gear train. You can assume them to be friction wheels. You can assume them to be gears with N2, N3, N4, N5, and 6 number of teeth. 3 and 4, they rotate as a whole. We call them compound gears. And if we define the input and the output, we want to know what the ratio of angular velocities between angular velocity input and angular velocity of the output is. Most authors, most textbooks look at the ratio between input and output as a transmission ratio. Some books take it the other way. They take the ratio between output RPM or omega and input RPM or omega. This means that a gear reducer will have a greater than 1 transmission ratio. Gear increaser will have a less than 1 transmission ratio. And vice versa if you're of the minorities that consider output RPM over input RPM the transmission ratio. Okay, so we want to know again what's omega 2 over omega 6 equal to as function of radii of the friction wheels. Remember now this, the friction wheels are equivalent to pitch circles of actual gears with teeth, and we're making use of the fact that the velocity of the pitch point, the instant center of 2 gears, is the same whether it belongs to, for the case of 2 and 3 would be, it's the same whether it belongs to 2 or to 3. Okay. So here I have the transmission ratio of the between gears 2 and the compound gear 3 and 4. So we have ratio between input would be to the group of 2 gears. So omega 2 input, omega 4 output. And if you write the velocity of the instant center, that will be omega 2 R2 from the perspective of gear 2, or we can write it R3 times omega of the group 3-4, omega 3-4. But we use the negative because of the known fact that this, let me use the pencil, so this gear is going to rotate. I make this thicker, will rotate the opposite, okay? So let me take this off. And so yeah, this is the first equation. And we can repeat it for other pairs. The other pairs of gears will be between 3, 4, and 5. And also shown, it's the ratio between, so transmission ratio omega 2 over omega 3 4 is also negative number of teeth of 3 over number gear 3 over number of teeth of gear 2. It's a little bit it's anticipating the discussion on involute gears, but essentially I could take this ratio R3 over R2 and multiply by 2 pi, so that gets me the circumference. So this is also equal, this part here, it's also equal to the circumference of the two circles by just multiplying with 2 pi both cases. Okay, 2 pi, 2 pi. Okay, now if I divide this circumference by what is called circular pitch, that is for, say, number 3 gear, I have one tooth and another tooth, and the circular pitch, actually they should continue below because we said this is the pitch circle. Sorry for this, I'm going to erase. And we define the circular pitch as the length of the arch between, and I overshot, so this is the circular pitch. I need to erase again. So the circular pitch, lowercase p, is going to be the length of the arch between one point and the corresponding point on the next gear. So if I divide the circumference by the circular pitch, it gets me the number of teeth. So all this to explain why this is also equal to the ratio of number of teeth. Again, minus sign, it's maintained to explain that, or make obvious that the direction of rotation of when you have external either friction wheels or gears, they'll be opposing to the input. Okay. All right, so the same we can write for the group 3-4, omega 3-4 would be, but what's meshing now is friction wheel 4 or gear 4 with 5. Same consideration, so it'll be this other equation. And then we repeated a group of gears 5 and 6. So we have 3 equations, and then what we're going to do is just multiply the 3 equations, and if we do so, we'll see that we have some, so essentially I have omega 2, 3, 4 times omega 3, 4 over omega 5, this other group, and then 5, 6, so 1, 2, and 3 coming from the respective equations. Let me take those off. Then I'll see that there's some, so they simplify out this one with this one. They cancel out or simplify out. So I'm left with omega 2 over omega 6. And then you see that there's also on the right hand side of the equation some simplification going. So I have R5 with R5 comes out. So really the number of teeth or radius of number 5 gear does not matter, other than reversing the direction of rotation. So this is called an idler. You see it in reverse manual transmission. When you switch in reverse, the motion goes through an idler. And anything else that's simplified? No. So it'll be ultimately I have minus, minus plus, another minus, so minus. So it'll be R3 times R6 over R2 times R4. So this is the final equation. And I could replace, it's not shown here, but I could replace what it's R with N's. So this would be the same as N3 times N6 over N2 times N4, same negative number. So this is a last equation. and we'll be writing it directly. There's no need to go through these steps. I just explained how we got it. So it's just a matter of if we're to find a input-output transmission ratio that is omega 2 over omega 6, you just go and say negative because it's external gearing, R3 over R2, and then I have negative because it's external gearing, R5 over R4. We're talking this other group, this and this, times negative again because I have external gearing would be R6 over R5. And of course you simplify like we did it here, and showing that number of teeth or radius of the friction wheel 5, it's not essential. I could make this smaller, the smallest possible. Let's see if I use this tool. So as long as I have contact between the two, and moving the axis of rotation here, so the same things happens. I'm just reversing the motion, but I'm not changing the total transmission ratio. So this is again an idler with smaller radius, your number of teeth that you could use. Okay, so this is for a simple gear or complex gear train, but just external contact, external gearing. Let's go to the next example. I don't save it. So this is where I have a gear train with an in-between shaft. You see this in some manual transmissions. And I have an input, direction of rotation of the input would be this one. Red is a better color. And I want to know what direction would be the output. I'm telling you now output rotation it's in the same direction. How do I know that? On one hand, you have direct drives on these lay shaft transmissions are called. So by just engaging or making them move as a whole, gear 2 and gear 5, you get the direct drive. But otherwise, I can show. So if the rotation is this one, number 3, and of course number 4 rotate the same, or opposing, but the same. And so goes in this direction, and output, it has to go in the other direction. As for the transmission ratio, I can just say, in virtue of what we recognized earlier, that would be omega 2 over omega 5 is just going to be negative because I have external gearing, and will be N3, number of teeth of gear 3 over N2, N2, and then times I have between 4 and 5 transmission ratios, again negative. I have N5 over N4, 4 that is, and the answer would be a positive value, N3 times, I'm not continuing writing, N3 times N5 over N2 times N4. Okay, so the plus sign indicates that the input and output rotate in the same direction, something that we knew already. Okay, next, number 3, that is, I don't save, is a compound gear train which has sorry, I wanted to select all, crop to make this bigger. So I want to know the transmission ratio between input and, again, want this to be red, input and output. which direction they rotate. Well, we can analyze just that, and I'm sure you did this in maybe high school. So one, the opposing direction, the same direction, this one opposing. So this is moving in this direction, the same as number 6 because it's internal gearing. Okay. All right, so how do we get a transmission ratio? We just write directly N3, it's negative because I have external gearing, it will be N3 over N2. And then I also have a negative transmission ratio going between 4 and 5, so driven gear number of teeth, that is N5 over N4. Okay. And then I have, so first, second, I have a third gear pair, and this is positive. And I have number of teeth of the driven gear N7 over N6. And negative, negative, positive, positive. So input and output going the same direction, something that we found earlier. And the end result, omega input, omega 2 over omega output, omega 7, or RPM. Either omega or RPM doesn't change it in any way. If there are friction wheels, of course, you replace N3 and 5 and 7 with the corresponding radii of the friction wheels. Again, to a gear, the friction wheel is equivalent to the what we call a pitch circle, and we'll discuss that in the chapter on involved gears. Number 4. Don't save. Here we have a transmission formed by a helical pair and a worm and a wheel pair. And I define the direction of rotation of the input, which is omega 1. We're assuming number of teeth of gear 1 as being N1, N2. I have N3, the number of starts of the worm. And here is, pay attention, here is important to know which direction is the helix of the, is it left hand or right hand, the helix of the worm. And then we have the number of teeth of the worm wheel. So we want to know, firstly, what is the direction of rotation? That doesn't come out from calculations like before because the shafts rotate in different planes. If I change the angle of the worm and the wheel, of course, they need to match. One is negative, the other one is positive, in order to have meshing about perpendicular axis. But if I mirror this pair, direction of rotation, it will be changed. So you need to know, part of the analysis, you need to know which, is it left hand or right hand, the worm. So I have the input, direction of rotation, and gear 2, which rotates together with the worm, rotating, opposing. And then imagine a corkscrew. Let's say this is it's not obvious. It's probably going to be on the right hand side. It will be a right hand side. So imagine a corkscrew, and imagine that you're holding the gear stationary. You turn the worm in the direction that is driven, and see whether the worm advances either away or towards, and then what you're doing, you just pull the corkscrew back in place and see what will happen to is the worm wheel going this way or this other way. the way it's the output is the way the output is shown is where the worm is right hand side. Is it right hand side? No, it's actually left hand side. So it comes out and I push it back in row. So as I turn it, well, I forget everything I said about the angle of the worm. So it's a right hand side in this direction. It comes out. I push it back in, rotates number 4, the worm wheel as shown. Well, it's opposing to this. I need to clarify, but again, having the at hand the pair, and you can inspect them, you can tell whether this is left hand or right hand. So this is a question, but otherwise the procedure would be like the one that I explained. Imagine you have a corkscrew, you hold the gear fixed, you turn the screw. Is it advancing away from you or towards you? You push it back in place, and what does the wheel do? At that instant, when you push it back in place, it acts as a rack and pinion. Anyway, so when it comes to transmission ratio calculation, the plus and minus sign does not make sense because they're rotating about axis, non-intersecting, and you have input over output, omega input over omega output is going to be N2 over N1, and I have N4 over N3, with N3 being number of teeth or at the starts of the worm. Okay, number 5. Number 5 is about planetary gears. This is a little bit different. It's not straightforward to understand. You haven't seen this before, so you may want to pay additional attention. One thing that we would like to, or I would like to discuss first, is on mobility calculation. So what is a planetary gear first? It's an assembly of gears with their shafts, but of the gears you have some that rotate or do a precessional motion, and you'll see a unit like this one, which is the simplest of the planetary gears, has mobility of 2. So mobility of 2, it means that I either have 2 input or 1 output, or 1 input and 2 output. Think of the differential, the car differential. So you have 1 input is the drive shaft on a rear-wheel drive truck. So you have the drive shaft, that's the input, and you have 2 output, the wheels. There's correlation between the RPM of the wheels due to the road. Or you can have 2 input if if I drive it, I do engine braking. Or other examples, there are some helicopters or armored vehicles like army tanks that use 2 engines, and the motion coming from the 2 engines is combined by the use of a differential, so that the 2 engines don't fight each other. It's in a sense the equivalent. Let me just illustrate this. So if you have a wagon, an ox wagon, and you have this is a pin, and you have 1 ox here pulling, and you have the other ox here pulling, and together they pull the wagon. This is the wagon, 2-wheel wagon. Okay, this is a pin, and what happens is, if one pulls more force is going to change the balance. You have to whip this other ox to keep up. There's also possibly, if you have a stronger ox than the other one, usually this would be the stronger ox, you'd make this ox's point where the back of the head is engaging this, I don't know how it's called, shorter. So you make for a stronger ox, you make this shorter, and for the weaker ox, you make this longer, a lever effect. But in any case, I have two inputs, and this is a 2 degree of freedom system. 1 degree of freedom is moving forward, the other degree of freedom is the pivoting. Okay, so differentials are the same. There are 2 degree of freedom systems. You either have 2 inputs and 1 output, or 1 input and 2 outputs. Let me reopen this, get rid of the oxen. Actually, I said number 5. It says 5. Oh, 5 is here. Okay, so I do have some like working model where I can show you. So it's gears and working model and planetary gears, and this is the simplest one. And let me make this small to where you can see. Okay, so there is a ring gear. We call it, this is the sun gear, this is the planet, and usually have at least 3 to share a load and also to balance dynamically the carrier or spider. It's also called, what's its other name? The other is planet carrier. Okay, crank or planet carrier. So back to the working model. We are having I have 3 motors that drive each of these. Actually, there are 2 of them, 1 and 2. So each of these bodies, the sun gear, the planet, the ring gear, the carrier, they have their own motors. If I hit run, then the unit moves, and not because one gear or piece pushes the other one, it's just because these are properly calculated. And here I have it to where the ring gear has 0 RPM, but you can have the ring gear, and you would see oftentimes planetary gears devised this way. So you have could be the sun gear, could be the ring gear. You can also fix the carrier, but that will turn this into a fixed axle transmission. And it's how they are used. For example, in a battery powered drill, in a battery powered hand drill, so I'm going to Peaks and Media, and I go to gears. Where's gears? And I have, okay, here's an example. Here I have a kitchen aid, kitchen mixer, and you see some gears meshing here. This bevel gear is just to deliver to the sort of power takeoff where it can put additional implements. But otherwise, you have the motors driving a reducer, and then you have this sun gear rotating. The ring gear is stationary, and motion is collected at the planet gear. This is how you get this processional motion to the mixer arm. Okay, but what I wanted to show you is the case of a battery powered drill that I took apart myself. And you see here the pinion, and here you have 2 planetary units, and you see common to the 2 units you have a ring gear, and the ring gear is stationary relative to the body of the hand drill. Okay, So this would be the sun gear of the first unit. The carrier, the first unit, it's part of the sun gear of the second unit. They both have ring gears and identical, and it helps for reducing the inventory or number of different parts for the assembly. So you have the first unit and its ring gear and identical ring gear, and they're solid to the or fixed to the ground. Okay. Anything else? Yeah, another view showing them my hand and the hand drill. All right, so we're going back to an example of, or there are numerous cases, numerous application of planetary gears. One is the automatic transmissions. They all use planetary gears. This is a Sturmey Archer. Is it 4-speed or 3-speed bicycle? And then the Ford T transmission used a let's see, Ford T trans. I'm trying to come on. Hey, it used planetary gear with brakes to get the 2 forward speed and 1 reverse speed. Another example would be the pencil sharpener mechanism. Its ring gear would be, as shown, and you're driving the arm carrier, and you have this time you have 2 planets, and the planets also act as the cutting bodies that sharpens the pencil. Example of an automatic transmission. With the planetary gears, so the planetary gears part of it looks like this one has 3, and then the most common of the differential gears or planetary gears would be the car differential. So you have the input pinion, a gear, we call it ring gear, same as with planetary gears, but this is part of bevel pair. And then you have the planets, and you have the 2 sun gears. Okay, so let's go back to the PDF or where the notes were. I closed everything. And the number, there's number 4. Number 4 screenshot that I took. So I said that we have relative to the ground, we have pin joints between would be so ground now we call it 0, it's body 0. So I have pin joint. It will be a multiple joint. I could, if you see here on the carrier number 4, I have here too. I have a pin joint between the ground and number 4. But I could move. I can mirror this shaft in the same direction, and I could have it on the. I could have it here. So instead of being the way it's shown, I could have it on the same side. Of course, it makes things more complicated. Not sure if you'll ever see one. Maybe they are out there. And then this would be the. I want this to be a bearing. So, and I have. So this will be the ground. I can use the pencil, and I want it thick or thicker. So these are the ground connections. Okay, so mobility analysis. Let's first count the number of bodies, and we're going to consider just on, remember the door hinge example or the toilet booster. We're not going to analyze, in mobility analysis is not going to include both of the planets, just one. So we have grounds as number 0 body, and then we have 1, the sun gear, 2 would be the carrier, 3 would be the planet, and 4 will be the ring gear. So 0 plus 1, 2, 3, 4 makes 5 number of bodies. As for joints with 2 degrees of freedom, that would be easier. So I have 1 here, again meshing teeth. They can do both relative rotation and relative sliding. So there are joints with 2 degrees of freedom. I have 1 here and 1 here. So there are 2. And now for joints with 1 degree of freedom, that is pin joints, there will be, let me change color. So there will be 1 here. There is 1. And then I have multiple of them in this, so 1 here. And then I have multiple of them in this area. So what do we see here? Joint with a multiple pin joint. So I see the ground, what I added, the crosshatch, the line with the crosshatch, so 0. And then I have number 2, the carrier. I have number 4, as well as number 1. Somehow it got lost, the labeling. So number 1, so 1, and we said 4. Okay, so 1 from before plus 1, 2, 3, 4 minus 1, 3. So 3 plus 1, there's 4. Okay, so mobility equation, 3 number of bodies minus the one that you fixed, minus 2 times joints with 1 degree of freedom, minus joints with 2 degree of freedom, and the answer is 2. So 2 degrees of freedom, again, you'd have to have 2 inputs, or you fix one element. And you can fix, you saw for the hand drill, the battery powered drill, this was fixed. You could fix the ring gear, or rather the sun gear, I'm sorry. So ring gear, sun gear, or you can fix the carrier, but if you fix the carrier, it turns it into a fixed axle transmission. Although possible, automatic transmissions may, some of them may have combinations where a unit turns into a fixed axle transmission. Okay, so analyze for mobility. What we have, what we want to calculate next is, so let me do this. Go back to this one without saving, don't save, and now discuss transmission ratio calculation. And transmission ratio, it's 2 parts of it. So you're firstly deriving general equations, and then you make those general equations particular to your case. So for example, if I want to analyze a unit where the ring gear is fixed, I'm not considering that fixed from the very beginning, only after I derive the full equation. So what is the governing equation, and what's the approach? One approach is what is called to do motion inversion. So motion inversion is to assume the world rotating in the opposite direction to the arm carrier, That's why you see here omega 2 subtracted, and that turns the whole, for the purpose of the analysis, turns the unit into a fixed axle transmission. So if I go back to the working model now, so what is motion inversion? Let me see, I do have one, maybe that's, so open, I have another, I have another one that's dual carrier, don't save. Gears, working model, planetary gears, this is the second one. Let's see, I left it with in the more general form. So let's see. Okay, so yeah, this one is where all elements rotate. These RPMs were properly calculated to where there's no, meshing is correct. If I just, if I turn this, so with sun gear 50, I make it negative 50, I make it 50, and hit run, you will see that the two starts overlapping. So again, it's not because the teeth push each other, it's because these motors, and there are 4 of them, have RPMs that are correctly assigned, and they match the number of teeth. They are listed here, 13, 11, 15. So this is a compound planet, and the ring gear 39. So I change it from negative 50 to 50. If I hit run, you see there is no longer correct meshing in this area of the planet planetary gear. So I change it back to, hey, come on, to negative, and now it's running correctly. And I open this up to where I can explain what motion inversion is. So we cannot write equations between the RPMs of the gears and the carrier and the number of teeth like right now. But if we turn it into fixed axle transmission, and we can do it in working model by just saying, so I need to go and select first the carrier. Okay, so I have the carrier selected, and then I go to view new reference frame on the carrier. See this I here? It's an option in working model, and now you're like riding on top of the carrier. So this carrier will appear stationary, and then the whole world rotates in the opposite direction. So I hit run now, and you can see the reference frame rotating in the opposite direction to the carrier, and I do have now a fixed axle transmission. So by subtracting omega of the carrier from all omegas here, we have our omegas, angular velocity vectors, are parallel, and they add as vectors. And if I subtract omega of the carrier from omega of all of the remaining bodies, I get valid equations that I can write between omegas again and number of teeth. So I could just say, let me stop this. So I could just say a transmission ratio between the sun gear and the ring gear will simply be, in the case of motion inversion, transmission ratio is going to be, that is 15 over 13 negative times 39 over 11 positive. So it's negative 15 over 13 times 39 over 11. Okay, and that's equal to what? That's equal to omega of the sun minus omega of the carrier over omega of the ring gear, again minus omega of the carrier, because I did this motion inversion. Okay. All right, so again, fixed axle transmissions, we can analyze for velocity, for transmission ratio. If we do motion inversion, all we need to do is just remember that we hypothetically assume an inverted motion equal to negative of omega of the carrier, and make sure you subtract that omega of the carrier when you write the equation. So let's go back to this one. And I think this other one was better because I squeezed the equations just a little bit. Okay, so going between, I said between the, and here we have a simple, not a compound carrier. So I go between the ring gear, sun gear, I'm sorry, and ring gear number 4. So it would be omega 1 over omega 4, but I subtract omega 2, that is the omega of the carrier, because I'm doing motion inversion. And I can just write in terms of number of teeth, negative would be N3 over N1, and then times would be N4 over N3, but plus because I have internal gearings or internal gearing. So there's a minus, and it would be a minus overall, but then I have number 3 gear, number of teeth of gear 3. This, you can call it an idler for the modified transmission with motion inversion. So this would be the governing equation. This is the equation for this gear train. Okay, and now I can just take it and do, for a particular application, say I can assume the case where omega 4 is 0, so this turns to 0, and I want to know what the transmission ratio is, say between 1 and 2. So from this equation you go ahead and say what's omega 1 over omega 2. Just a little bit of an algebra. You would say, so equals to what? Again, this would be the case where omega 4 equals 0. Okay, one scenario, like in case of that battery powered drill. So I have omega 1 from this equation over negative omega 2, and then I have plus 1 equals negative N4 over N1, and then to get omega 1 over omega 2, I move 1 on the other side, and then I need to remember there's a minus here, and essentially got it. So omega 1 over omega 2 is just going to be 1 minus what are the plus N4 over N1. Problem solved. Or I could have, again, 2 inputs. I can have the sun being driven by an electric motor of 1750 RPM. I can have the ring gear being driven by something else at 800 RPM. This equation with omega 4 not crossed out would be the starting equation, and I would like to know what omega of the ring gear is, and there you have it. You can also write partial equations. You saw the kitchen mixer, and the output was the actual planet. So if the output is the actual planet, let me open again number 5. File, open number 5 again. Don't save. So if I want to know what, if my concern is what omega 3 equals to, I can again use motion inversion, and I can say, in addition to this equation that allows me to, and for that kitchen mixer, omega 4 was 0. So, but in addition to this equation, I can write, again, motion invert. I can write the transmission ratio between 1 and 3. So it will be omega 1 over omega 3, okay, minus carrier omega because I do motion inversion, okay, and this is going to be negative N3 over N1. Okay, so I have a second equation, and if I'm interested in knowing what omega 3 equals to, I could just work with the two equations, make omega 4 equals 0. That's the case of the kitchen mixer. I know what omega 1 is, allows me to calculate omega 2. So again, omega 1 should be, the input should be given. We're doing analysis. Omega 4 equals 0. And this allows me, this first equation allows me to calculate omega 2. I come into this equation with a known omega 2, and I can solve for omega 3. Again, omega 1 is the input. It's known. So again, I discussed the case of the, actually I need to go to back all the way to Pixel Media, and where I have, what was it, gears. I'm projecting back, hey, gears, that is, the kitchen mixer. Okay. So I'm going to end this recording shortly. Email me, please, your questions. Don't wait until the uncertainty or the unknown becomes stringent, and including what do you want me to share with you of, the Barry Power Drill photographs that I took. This one I bought for a few hours, kitchen mixer, put the box without opening it on the scanner and return it a few hours later. Just because of this, I found it interesting, this photograph. What else do I have here? Examples of worm and wheel and bevel gears. And actually, since we're here, we can discuss gear manufacturing. So we're not, this is an exploded view. There's an exploded view of a planetary unit showing the bearings, the ring gear, that it will be flanged, so it means it's stationary. Many applications have the ring gear fixed to the ground. So I said we can discuss gear manufacturing, and actually gear manufacturing, I do have better material with the notes, and I have some videos. So there are a number of processes used to fabricate gears. One is form cutting. So there's a little video. I hope it's not conflicting with the recording. It looks like it does, or did it? So you're just using a form cutter that is an end mill, and you remove the material to where you generate the flanks of the I need to get out of this. Hey, come on. All right, so that was form cutting. Planning, let's see if I use a different, so open with movie and TV. What else? Windows Media Player. Maybe this would be better. I hope they're not conflicting. Yes, so it's better. So Windows Media Player, that's better tool. And you see reciprocating cutters. and they're slowly removing material off the blank, and then we do have shaping with the, and I said no, better tool, or the better would be the, well, choose another app, and it'll be Windows Media Player. Always use Windows Media Player. Okay, so the shaper tooth tool, or shaping process, it's called shaping. And hey, now we have an issue, some conflicting. Well, here's another one. Maybe this one is working. Or maybe if I look at the photograph. Alright, so what you're seeing here, it's a photograph of the shaper in progress, shaping process. And this is the future gear, the blank. This is the cutter, and it does a sort of planetary motion around the blank, the future gear. And then the most productive process, again, this is for milling. You just have an end mill that removes the material and it forms the tooth. The problem is that you would need a different formula for a different number of teeth because their geometry changes. So you can use the same tool for, say, plus minus 1 tooth. So if this is made for 35 teeth, you can use it for 34 and 36, allowing for some imperfection. And then the most productive one is productive because of the it's continuous. Removes material continuously versus the shaper, where the, let's try again, open with, does it work? No, I did something, there's some conflicting. Okay, probably if I stop the recording will work. Okay, so in the shaper, as it's visible on the movie, and you can look up YouTube's showing the various process for gene generation. So when in the downstroke, it engages, the tool engages in the downstroke, the tool engages the blank. For the return stroke, it does an away, it moves away, and to where it's not engaging the material. So that's it makes the process less productive because only half of the time I remove material. Okay, I can use, and this will be last, I can use the animation or the simulation, working model simulation, to demonstrate that process, how you can generate a ring gear using the planet as a tool. So what I'm going to do, I go to Object, where is it, View, and so word tracking, yes, tracking every frame. All right, and then I can say the window appearance off, including this one. I don't want to go with window appearance off. Okay, and then let's go to tracking every frame. So let's see. Edit, select all object, or where is it? Word tracking off, and then only this one. Word tracking every frame. Let's see now. Run. No. I said I want to track this body. Window, okay, property, track outline. and I don't want to track this. Don't track. Edit, actually edit, select all, window, appearance. Oh, maybe now. Let's see. Okay, so I'm generating a ring gear using a with the shaping process, and this will be the tool. Inside of the machine, I need to do a setup to where the tool is synchronized to where I'm generating the right number of teeth, and the correlation between the blank geometry and what happens inside of the machine, should be based on number of teeth of both the tool and the future gear. Okay, when discussing envelope gears, we'll look at a dedicated application where you can even change the number of teeth. Conversely, I could where is it? Erase track. Okay, I could also turn this off. Window, appearance, show, and then let's see, run. What do we need to do? Erase track. I believe okay. So if I go to world and or rather view, new reference frame, move on the carrier, it becomes a fixed axle. So no. Sorry, this wasn't prepared, but again, I will play them for you. There are good sides on being able to, or teaching online classes. So I have dedicated applications. I have them. I can show them to you. Okay, so let's go to this will be just, don't save, let me clean everything here. Appreciate your patience. So I'm going to just, since we discussed the manufacturing processes of gear, so I go to teaching, and for this class, and I go to notes, and I go to gears, come on, and the working model part, it has gear generation, and I think this is it. So gear generation, as you can see, I can change the number of teeth, and this is set up to generate teeth for the for external gears. I hit run, and I did generate a what I tried earlier. Wasn't prepared for that, but again, I have a dedicated, as you can see, working model. So I was able to produce an external gear. Here it says for external gears, N should be greater than 2. For internal gears, N should be greater than, and I need to make it negative. So if I make this negative 26, say, my application is going to envelope a ring or internal gear. Okay. And again, it's for any number of teeth. So if I make it 31, I get 31 number of teeth. Really was the earlier what you saw, simulation of a planetary gear, but now the RPM of the motor is correlated to where I get the number of teeth that I desire. Okay, so if I change this to 17, now I do 17 teeth external gear. Okay. All right, well, this being said, I'm going to just stop here recording, and we'll discuss more about, in a separate recording, about the project.